Okay, so let's go ahead and get started. For those of you, I guess everyone was probably here on Tuesday. If you weren't, I did hand out a syllabus. You can find it on the course website. You can find the link to the course website on the syllabus. So hopefully, okay, that was a joke. You can probably find the course webpage yourselves. The syllabus is there. One announcement. Well, two announcements really. I just handed out the first problem set. It's probably a little easy compared to some of the problem sets later on in the semester. It's only 3 pages long, so you know. Actually, don't be too scared. Most of that's explanation and fluff. Okay, so it's not actually, I think, a super long problem set. Mostly it's review, a chance for you to get to remember a few things from quantum mechanics, a few things from electromagnetism, get some practice with Einstein summation notation and manipulating field equations and things like that. Okay, so it shouldn't be too hard. But the other announcement that I want to make is, as I mentioned yesterday, I am unfortunately going to have to miss class on Tuesday. So that would be next Tuesday, September 15, September 15, which is next Tuesday. Sorry about that. I mean, I usually don't like to miss class, especially so early in the semester. There was nothing I could do about this one. This is something that was on the books for a year and a half. So sorry about that. And I will be scheduling a makeup class at some later time. Okay, and probably what I'll do is I'll also send out an email announcement reminding people that there's no class on Tuesday. Good. Okay, so let's just go ahead and pick up where we left off last time. So let me just remind you of our conclusion at the end of last class. So we concluded that there is no consistent single particle theory of quantum mechanics that is consistent with the laws of special relativity. So in particular, we saw that it's impossible to have a single particle theory of quantum mechanics consistent with special relativity. And what we did is we studied the solutions to the wave equation. So this was Schrodinger's equation for the quantum wave function psi as a function of position and time. And we set it equal to the Hamiltonian, which is the energy operator not of Newtonian physics, but rather the energy operator of special relativity. So here, this was the Hamiltonian of the single particle relativistic theory that we were trying to construct, which was, so in special relativity, the energy of a particle is the square root of m squared c to the fourth plus p squared c squared. And so that led us to naturally guess the appropriate special relativistic generalization of the Hamiltonian of quantum mechanics. Okay. Now, as usual, I'm going to use units where c and h bar are equal to 1, but in this equation I included my c's and h bar mostly for dramatic effect, I suppose. Okay. And if you remember the derivation that we went through last time, we saw really that the problem arose because we had the square root. Okay. Remember, I gave you this argument where we computed the probability for a particle to travel a distance r in a time t, and I used some contour manipulation, and the fact that there was a square root here led to a branch cut, and it was by studying the properties of that branch cut we saw that in fact you had a non-zero probability to go faster than the speed of light. And indeed, if you look at this equation for a second, you can see that although I claimed that it was consistent with special relativity, there's something deeply non-relativistic about this equation. Okay? Remember that the whole point of special relativity is that space and time are treated on equal footing. There are symmetries, Lorentz transformations, that mix the space and the time coordinates. Whereas you see in this equation, I'm treating space and time quite differently. In particular, I have a time derivative here that is not under a square root symbol, but The spatial derivatives are squared, and then I'm taking a square root. Okay. So what we would really seek is some sort of formulation where we treat space and time on equal footing. Okay. And one way to do that would be to simply square the differential operator that sits on both sides of this equation. So, in particular, you could ask whether it's consistent and sensible to write down a theory of quantum mechanics where you have a wave function where instead of the first time derivative of the wave function being equal to that Hamiltonian, instead the second derivative of time derivative of the wave function is equal to the thing that you get. Sorry, is there a square there? There's a square there. The thing that you get when you square that relativistic Hamiltonian. By the way, if I make some stupid mistake, like forgetting to square a h-bar or something like that, please feel free to interrupt me. And also, please do feel free to interrupt and ask questions. Okay. So this is a very natural equation to write down. Indeed, this equation treats space and time in a much more democratic manner. The left-hand side and the right-hand side both involve squares of time and spatial derivatives. Okay, so this is something that looks much more consistent with the idea of special relativity. And indeed, this is one of the most famous equations in physics. It's known as the Klein-Gordon equation. In particular, it's known as the massless Klein-Gordon equation. Actually, no, sorry, there's a mass term there. So it's just known as the Klein-Gordon equation. In fact, there's an interesting piece of history here, which is that the Klein-Gordon equation is called the Klein-Gordon equation because it was discovered by Schrödinger, of course. In fact, he discovered it before he discovered the Schrödinger equation that you know and love. He was looking for an equation that was obeyed by the quantum wave function, and he knew about special relativity, and so he wrote down this equation that I've written here. But he didn't actually ever publish it. So in his published paper, he only used the non-relativistic version of the Schrödinger equation, which is something that you know and love. Because, in fact, it turns out that if you try and interpret the equation that I've written here, the Klein-Gordon equation, as an equation for a quantum wave function, it turns out that it really makes no sense. Okay? So this is an equation which is consistent with special relativity. But it does not make sense as an equation for a quantum wave function. So indeed, we are going to spend some time in this course, and even in this lecture, studying the properties of this equation. But the important thing that you need to remember about this equation is that it is not going to be an equation for a quantum mechanical wave function of the sort that you study in your quantum class. Okay. Why is that? Well, let's just remember, what does a wave function do for a living? Okay. Why are we interested in wave functions? Well, the physical interpretation of a wave function is that if you take a wave function and take its absolute value squared, that's supposed to compute for you a probability. Okay. In particular, this p of x, which is the square of the wave function, I guess I should call it p of x in t, is the probability density that your particle is sitting at a point x. So it's a probability density. And in particular, the important feature that a probability density should have is that it should be that if you integrate it over all space, it should be equal to 1. Okay. And in particular, it should be independent of time, right? So probability, so one way of saying this is that probability should be conserved, okay? Or another sort of less melodramatic way of saying this is that the probability that your particle is somewhere should be equal to 1. Otherwise, you have a particle that's disappearing or reappearing or something like that, okay? And so, indeed, if you take the usual non-relativistic Schrodinger equation and you study the integral over all space of the square of the wave function, and you take its time derivative, then it's quite easy to see that, in fact, the time derivative of the integral of that probability density is equal to 0. So it's independent of time, and so if the the total probability is equal to 1 at time t equals 0, it's going to be equal to 1 at all later times. So, I mean, that's easy enough to go through. I mean, you just imagine, you know, you hit this guy with d by dt, you plug in Schrodinger's equation, you do some integrating by parts, and it's equal to, and you get that the time derivative is 0. Okay. Have you guys seen? I assume you've seen that before. Have you seen that argument before? Okay. Maybe not. Okay. If you haven't seen that argument before, you should see it. Okay. So you'll see it right now. So in particular, if you just take the time derivative of the total probability density, p of x and t. So what is that? That's the integral dx of the time derivative of psi star psi. And then you plug in Schrodinger's equation. What is Schrodinger's equation? Schrodinger's equation says that I h bar d by dt. Okay, h bar is equal to 1. We'll never get anywhere if h bar is not equal to 1. So I d by dt of psi is equal to minus d by dx squared, or the gradient squared of psi, plus, say, some potential times psi. So you just take the Schrodinger, you just take that time-dependent Schrodinger equation and its complex conjugate, and you plug it into this equation here. Okay. First, let's look at the v term. So you have the d by dt of psi is equal to minus I times v. So when you hit that d by dt on psi star, you get plus I times v. When you hit that d by dt on psi, you get minus I times v, and those two terms cancel. Okay. And similarly, if you look at those derivative terms, if you do the first term, you get on d by dt acting on psi star gives you I d by dx squared psi star times psi. The second term gives you minus I psi star d by dx squared on psi. Then you integrate by parts twice to move the d by dx squared from psi star to psi. Those two terms cancel. Every time you integrate by parts, you get a minus sign. So if you do it twice, you get a plus sign. Okay, so that's equal to 0. If that was a little fast, go through when you're, trying to fall asleep tonight and do it again. So, and this is, the whole point of quantum mechanics is that the wave function is something you square to get a probability density. Okay? But it was crucial here that Schrodinger's equation was linear in time derivatives rather than quadratic in time derivatives. So if psi obeys the Klein-Gordon equation, the integral of p over all space is not conserved. In particular, it's not a constant in time. Okay. So that means that it makes no sense whatsoever to think about the Klein-Gordon equation as an equation for a quantum mechanical wave function. Any questions before I continue? Please feel free to interrupt me and ask questions. If nobody asks questions, eventually I'm going to start asking you questions. So let's step back a little bit and think about what might be going wrong here. Okay? The problem, really, is that we're still not treating space and time completely democratically. We're still not treating t and x as exactly the same on exactly the same footing. So in particular, if you think about single particle quantum mechanics, then what is X? Well, X is an observable. Okay. That is to say, in quantum mechanics, it is an operator, so some sort of Hermitian operator acting on a Hilbert space. But T is not an operator. It's a label. Okay. It's a label that we use to parameterize different operators. So, for example, you know, the operator that measures the position at time t equals 0 is one operator. The operator that measures the position of the particle at some later time is a different operator. And so X is an operator and T is a label. Okay? And so clearly we're not treating these things on the same footing. So instead, in quantum field theory, what we really do is we treat both of these objects, space and time, on the same footing. Space and time are both labels used to parameterize operators. So what does that mean? That means that the observables in the theory are going to be functions of both space and time. In the same way that in quantum mechanics your observables are a function of time, the observables are functions. So a label that we often use would be the label phi for one such observable. So and they're functions of space and time. And we usually, the name that we usually give, oops, okay, my power adapter, something just happened to it. Okay, the battery might run out. Let's see. Okay, the name that we usually give to such an observable is a field. So, whereas in normal quantum mechanics, if you want to think about field theory in terms of normal quantum mechanics, then quantum field theory is like a quantum mechanics system with an infinite number of degrees of freedom. One per point in space. Remember, usually in quantum mechanics or even in classical mechanics, a degree of freedom is something that you use to characterize your system, a variable that's used to describe the state of a system that's a function of time. And here, a quantum field theory is, or a field theory is a dynamical system where you have one such degree of freedom for each point in space. Okay? And it would be the value, say, of some field phi at the position x. And of course, you already know a field theory. In fact, you already know a couple different field theories. One simple field theory, although not the simplest field theory, but one simple field theory is electromagnetism. What are the observables in electromagnetism? The observables are the electric field and the magnetic field. So, or if you want to formulate the theory not in terms of the electric and magnetic field, but in terms of the electrostatic potential and the vector potential, then we typically organize them into a four-component object that I'll call A mu, whose four components, well, the first component is the electric potential phi, also called V sometimes, and the other three components are the vector potential A. In fact, you already know what wave equation the electromagnetic field satisfies. You probably spent a year studying it. in your classes on electromagnetism. And it turns out that in an appropriate gauge, okay, so you probably don't know exactly what the words an appropriate gauge mean yet, but you will. So you can just take this to mean with an appropriate choice of variables, which is something we'll spend quite a bit of time studying later on in the semester. Maxwell's equations, that is to say the equations of motion of electromagnetism, obey the Klein-Gordon, say that the potentials A obey the Klein-Gordon equation. In particular, they obey the massless Klein-Gordon equation where that parameter m was set equal to 0. So you're probably most familiar to this in electrostatics, where, remember, you probably saw that the electric potential V obeys the Dirichlet-Bershon equation. I think that's usually what it's called. You guys have seen this, hopefully. This is where electromagnetic waves come from, right? It's because the electromagnetic potentials satisfy a wave equation. And in fact, that wave equation is nothing more, nothing less than the Klein-Gordon equation that we saw earlier. Okay. So don't worry if you don't remember precisely the formulation of electromagnetism as a field theory. You're going to go through it in a great deal of detail on the problem set that I just handed out. That's due next Friday. Okay. And you'll remind yourselves of all of these sorts of things. And of course, we're going to spend quite a bit of time later on in this course sort of unpacking all of these details about electromagnetism, both classically and quantum mechanically. But the point that I really want to emphasize is that the Klein-Gordon equation should be viewed as a classical wave equation not as an equation for a wave function. In the sense of quantum mechanics. So what I'd like to do now is talk a little bit more in more detail about classical field theory. That is to say, dynamical systems where you have an infinite number of degrees of freedom, 1 degree of freedom for each point in space, before moving on next week to the quantization of these systems, where we'll understand exactly what it is classical field theories have to do with particles and why, when one quantizes one of these classical field theories, one ends up with propagating particles. I mean, you can already sort of probably see intuitively where this is going. As you know, Maxwell's equation, the equations of motion of electromagnetism, have propagating wave solutions. Okay? They're electromagnetic waves. And when you quantize the theory, the quanta of those electromagnetic waves are particles. In the case of electromagnetism, they're photons. In the case of some other field, there'll be other sorts of particles. Okay? So what I'm going to do now is embark on a little bit of an introduction to classical field theory. Before I do so, let me pause and see if there are any questions. Yes?
I don't, and probably this is absolutely not relevant, but you never said why the Klein-Gordon equation got its name. Is that interesting at all?
Guys in Klein-Gordon, I suppose. Yeah. No, I don't know. I mean, the interesting thing is that Schrodinger actually discovered it first, but because he couldn't come up with an interpretation of it, he never wrote a paper on it, as far as I understand. I mean, yeah, Klein was a quite famous physicist. I don't actually know much about Gordon, but yeah. Good question. I don't actually know the answer, though. Any other questions? So, what I'd like to do is spend a little bit of time just discussing classical field theory. Now, classical field theory is a subject about which you already know a fair bit. I mean, you took a whole course on Maxwell's equations and stuff like that. Instead, what I want to do here is focus on, just so that we can, this is the simplest system that we could imagine, which will be much simpler when we want to try and quantize the theory. I'd like to consider a much simpler classical field theory today than the electromagnetic field. Okay? The electromagnetic field is really a set of 4 quantities, those 4 potentials, or the 6 field strengths, the electric field and magnetic field, if you like. And because of that, it has some kind of complicated Lorentz transformation structure and a lot of indices floating around and stuff like that. So instead, for the first part of this course, when we're really trying to understand the basic structure of quantum field theory, we're going to focus on a much simpler example, which is known as a scalar field. So the picture that I want you to keep in mind when we talk about a classical field theory is I want you to imagine that you have some sort of lattice, okay? And it could be some sort of atomic lattice, okay, some sort of material. And we have a lattice of particles connected by springs. Okay. That's an awfully sort of mechanical analogy. If you want to think about it differently, you could think about an atomic lattice where the individual points of the lattice are atoms and they're held together by some potential that binds them, that attracts them to one another. Or you could think of, well, you could think of it in terms of a crystal of some sort or anything like that. But the simple mechanical model that you want to keep in mind is some sort of lattice of particles, okay? Now, I'm not going to draw an infinite two-dimensional lattice, but you sort of get the idea. Okay, there's the picture. So so we want to characterize the positions of the particles in this lattice. And what I want to do, just to keep life simple, is I want to forget about the motion of these particles in the plane of the lattice. And I only want to talk about their displacement in the direction perpendicular to the lattice. Okay? So let's let QA of t, so this is going to be our degree of freedom, it's going to be the displacement of the 8th particle in the vertical direction. So here I'm imagining a very simple two-dimensional lattice of particles, and Q is going to be the vertical position of one of these guys. And A here is just a label for the different lattice sites. This is just a very simple mechanical model that you can use just to keep a picture in your head of what a field theory really is. So, of course, we now want to describe the dynamics of this system. So, as usual, to describe the dynamics, we should minimize an action, so we should write down a set of equations of motion. And as you know, one very simple way of summarizing the equations of motion of some system is to write down an action and so the dynamics are determined by some action that's some function of the Q variables, the dynamical variables QA. Sorry, I guess I put a lower index there. And that action will be the time integral of some Lagrangian, which will be a function of Q in its first derivative. And then, just as a reminder, this is something you all know, the equations of motion are found by looking for the, so the equations of motion are found by minimizing the action with respect to variations of these degrees of freedom. So you vary the dynamical variables, and demand that the the variation of the action to first order and the variation of the degree of freedom is equal to 0. But that's Euler's principle, and the equations of motion that you get are the Euler-Lagrange equation. So let's just remember how we go about deriving these equations, because I'm going to generalize it to the case of field theory in just a few minutes. So the way that we do this is you imagine that you have this action, and you now want to imagine varying the degree of freedom Q. And what do you get? Well, so that's the integral of the variation of the Lagrangian. So the Lagrangian depends on Q and Q dot. So you have dl by dqa times delta qa plus dl by dqa dot. Sorry, I'm mixing my indices. Qa dot times delta qa dot. Okay. And then you integrate that guy by parts. So this is the integral dt times dl by dqa minus d by dt of dl by dqa dot, all times delta qa. Okay. All I've done is I've integrated by parts and moved the time derivative from here over to here. Okay. And when you do that, you actually get a total derivative term from that integration by parts, which is dl by dqa dot times delta qa. Any questions on that? Is that more or less clear? This is something that you've seen, presumably, in all of your classical mechanics classes. And the idea, then, is that you look at a variation of the field that vanishes in the far past and the far future, so that when we integrate this total derivative, that's the fundamental theorem of calculus, if the quantity here vanishes in the far past and the far future, the boundaries of integration, we can ignore that and set it equal to 0. And then the statement that the variation of the action vanishes at first order in the variation of the degree of freedom Q is the statement that this quantity here must be equal to 0. Okay. So the equations of motion are the Euler-Lagrange equations, dl by dqa minus d by dt of dl by dqa dot is equal to 0. Any questions on that? I mean, I went through that rather quickly because, well, it's something that you should all, that's the sort of manipulation that you should all become extremely familiar with if you're not extremely familiar with it already. So if, sometimes people get confused by the integration by parts and moving the derivatives around and so on and so forth. Again, when you're having trouble falling asleep tonight, that's the derivation you should go through. Good. So in order to describe the dynamics of my lattice of particles all connected by springs, I'm going to need to tell you what the action is. Okay? I'm going to need to tell you what the Lagrangian is. And for our system, just to start, I would like to start with a very simple Lagrangian. Okay? So what I'd like to imagine is that for each of these particles, I have a mass. And so you have kinetic energy, which is 1/2 mv squared, okay, where v is the velocity in the direction perpendicular to our lattice. And then you have some potential that depends on the positions of the various particles. And I'd like to just take a leading approximation where we assume that the particles are all very close to their equilibrium configuration, which is, say, at qa equals to 0. And so that means I can expand this potential in powers of q. And the first term in the expansion in powers of q will be quadratic in the q's. And then there'll be higher order terms which are cubic in the q's, quartic in the q's, and so on and so forth. Now, of course, you could also have a constant value, but the constant isn't actually going to matter. As usual, one can always shift the energy to get rid of the constant. One also isn't going to have a linear term in the q's. Okay, who can tell me why you don't have a linear term in the q's? Anybody? Yes. Good. So that's the statement that you have an equilibrium configuration. Good. Okay. So to make life simpler, what I'd like to do is just imagine that we have only a sort of nearest neighbor approximation. So that the only q's where this KAB will be non-zero are when the two particles are right next to each other. So what does that mean? That means that V will be the sum of two terms. So you'll get a term that looks like the sum over A, QA squared. Okay. So that just describes some potential, some restoring potential that makes these particles want to all sit at QA equals to 0. Okay. And then there'll be some quadratic interaction between the two, so some sort of sum over A and B, where the A and B describe neighboring lattice sites of QA minus QB quantity squared. And I'm actually using a little trick here. Okay, so I'm using the fact that QA QB is equal to QA minus QB squared minus QA squared minus QB squared. Okay, and I suppose there's a factor of 2 there. Good. So this is going to be the leading contribution to the potential if you only allow these nearest neighbors to interact. Okay. So in fact, this system is a quite well-known system. It's a very sort of famous model for crystals and for solids with a lattice structure. It's known as the Debye model. You've probably seen it already. I mean, I'm assuming you guys have seen this before. If you haven't seen it before, don't worry. You'll work out both the classical and quantum dynamics of the system in the problem set. Okay. But the important point is that, as you'll see, this system has traveling waves. This is something that you'll work out. So this just describes, if you imagine you have a lattice of particles all connected by springs. If you displace one here, that'll cause some propagating wave solution to propagate out. And in the present case, those propagating waves are known as phonons. Okay. Essentially, they're sound waves, hence the name phonon. Okay. So far, I'm not doing field theory at all. I'm just doing quantum mechanics. I'm doing a quantum mechanics with a large number of particles, but it's quantum mechanics nonetheless. But what I'd now like to do is I'd now like to imagine that we only care about the system on length scales that are long compared to the lattice spacing. That is to say, long compared to the distance between two adjacent lattice sites. That means that we can approximate QA of t by Q, so we can, instead of using the label A to label the different positions, we can just label them by the position on the two-dimensional lattice X. So all I'm doing is I'm changing my labels. So here we really have 1 degree of freedom per point X. Now, of course, there are a continuously infinite number of points on the plane, whereas previously I was talking about a lattice with only degrees of freedom sitting at discrete points. But the idea is that as long as you only care about observables that on length scales that are very, very long compared to the lattice spacing, these two things are effectively the same. And indeed, I'm no longer going to use Q to describe my degree of freedom. I'm going to rename it phi, which is the traditional name for a scalar field. So indeed, the scalar field that we were talking about earlier that obeys the Klein-Gordon equation is nothing more or less in the simple model than the lattice, the displacement of some particle that's sitting on a lattice. And indeed, I really would like to encourage you, whenever I hand you some sort of new classical or quantum field to study, I really want to encourage you to think about that in your head as space really being a lattice of points. And the degrees of freedom, phi of x, are really just one degree of freedom per point in space living on some lattice. Okay? You can often clear up a lot of confusions you have if you think of space as a lattice. Okay? Now, there are some situations in which this is a very bad thing to do. You can be misled sometimes. But at least as an intuitive picture of what quantum field theory is, it's usually a good idea to think of space as a lattice. Okay? And the only point being that we're interested in observables that involve length scales long compared to the lattice spacing. Yes, question. Well, the reason why it's there are a couple of reasons why it's a bad idea, which is that the lattice has symmetries that are different from the symmetries of actual space. Okay? Space has continuous translation symmetries, and a lattice has discrete translation symmetries. So in the limit where the lattice spacing becomes very small, those discrete translations become the continuous translations. So that's okay. The real problem is when you start talking about special relativity, and you talk about boost invariance. Whereas it's easy to construct a lattice which in a continuum limit reconstructs translation symmetries, it's very difficult to find a lattice which in a continuum limit reconstructs the boost symmetries of special relativity. In particular, if I hand you a lattice and I do a boost symmetry, that changes the lattice spacing, right, because of length contraction. So it's situations like that where you can get a little misled. Good. Excellent question. Other questions? Good. Okay. So what I want to do now is I want to take that action that we wrote down above and rewrite it in terms of this field variable x, and then reconstruct the Klein-Gordon equation as the equations of motion of this field. So let's start with the kinetic energy. So what was the kinetic energy? It was 1/2 mv squared. Okay. So what is that? So the sum over A now becomes an integral over x. So here I'm imagining a lattice in 2 dimensions, although I could of course easily imagine some sort of lattice in 3 dimensions where I have some degree of freedom associated with each lattice site. And so you have an integral d squared x d phi by dt squared. And there's a coefficient there, so you get a factor of m coming from this factor here. But of course, when I take that sum over A and write it as a d squared of x has units of length squared, so I'll need to put something with units of length squared there. The easiest thing to do is just to take L to be the overall length scale of the lattice and divide by L squared there. But it really doesn't matter. I mean, I could absorb that into my definition of the field variable if I wanted to. So at the end of the day, there's some constant there whose value is not too important to us. And so I'll just, for the time being, well, we could call it sigma. Because if you were, well, okay, let's just call it sigma. Okay. Because it's related to, if we were studying a propagating string, it would be related to the tension of the string. Or if we were studying, say, if this were some sort of sheet, and we were studying the dynamics of the sheet, then sigma would be the tension of the sheet. Okay, the tension is another name for the thing that quantifies the restoring force of a sheet towards equilibrium, some sort of rubber sheet or a rope or something like that. Similarly, the potential term, V, what did you get? Well, you had QA minus QB squared, where A and B were neighboring lattice sites. Okay. So what is QA minus QB in the language of this field phi, where A and B are neighboring lattice sites? Anyone have a guess? It's the derivative. It's the second derivative, because we have a square of the field with respect to x. Okay. Where here, I'm taking the derivative in the direction of the lattice displacement between A and B. Good. And again, for dimensional reasons, x has units of length, so I'll need to put some sort of dimensional constant length squared there. So what is the action then? So the action, which previously I wrote as a function of the q's, is now a function of the field variable phi, and it's integral d2 dt of the Lagrangian. But the Lagrangian itself is going to be an integral d squared x of something else that we usually call curly phi, which is the Lagrangian density. Write it like that. Where the Lagrangian density is 1/2 sigma times phi dot squared minus, well, let's just call it rho times d phi by dx squared, where rho is, well, I guess I wasn't very specific as to what this constant is, so there'll be some sort of spring constant there. And so rho will be something like kappa times L squared. And then you'll have a similar term, so that comes from displacements in the x direction. Then you'll have a similar term coming from displacements in the y direction, if this lattice is spread in the xy plane. And then you'll have something proportional to phi squared coming from this term right here. Okay, so that's just going to turn into an integral d2x of phi squared. And then you'll have other terms coming from higher order terms in the potential. So let's write this all a little bit more succinctly by doing the following. So let's just reabsorb that factor of sigma into our definition of phi by rescaling phi to phi over the square root of sigma. Then the Lagrangian is 1/2 d phi by dt squared minus c squared times the gradient of phi squared minus m squared phi squared plus higher order terms. Where here c is just the name that I'm giving to whatever combination of rho and sigma I get here. I guess it's like c is the c squared is rho over sigma, and similarly m is just the name that I'm giving to whatever combination of tau and sigma I get. So I get, m squared is like tau over sigma, and so on and so forth. Okay. So just to summarize, on length scales that are very long compared to the lattice spacing, we can describe our system as a theory with 1 degree of freedom per point in space-time. And the dynamics of the system is determined by minimizing the action which is the integral d3x of the Lagrangian density that's a function of phi as well as its derivatives. The parameter c that I have introduced here has units of velocity, and remember the excitations of this system are phonons, and so it won't surprise you if I tell you that c is the speed of sound of the traveling wave solutions. So all of this was really just a sort of simple mechanical model for a classical field theory. Many of the field theories that we'll be interested in this class don't really have simple mechanical models like this. Okay? So this theory that I've written down is called the scalar field theory. And indeed, there are many examples of scalar field theories in nature. One example is the Higgs boson that describes, the excitations of which the particles of which were recently discovered. Another example of a scalar field in nature is the inflaton, the conjectured field whose energy density and dynamics governs the expansion of the universe at very early times. Another example of a scalar field would be the field whose particles are the Cooper pairs, whose dynamics describe superconductivity. So scalar fields appear all over the place in nature, but it's not the case that they always necessarily have a simple origin in terms of a mechanical model like this. Okay. So the typical scalar field theory that we'll be focusing on most in the class is indeed this scalar field theory that we have here, but instead promoted to live in 4 space-time dimensions, 3 space and 1 time dimensions, with a Lagrangian that is, as I have written up here, except now that gradient involves 3 spatial gradients rather than just 2 sets of spatial derivatives. And as usual, I'll be setting the speed c here equals to 1. So in the mechanical model, c was the speed of the phonons, the speed of sound. In relativistic field theories, of course, c will be equal to the speed of light. Good. Any questions on this so far? Yes?
This question about the derivation. When we have our new action, we have an integral over space, d squared
Correct.
x. Now in the kinetic energy, I can see that integral term present, but I don't see it in the potential. So where does it come from there?
Where does this term come from?
Further up.
Sorry, yes.
Sure. Okay, so here we have s of q is integral dt, integral d squared x. of
Yes.
Lagrangian.
Mm-hmm.
Now,
Where does it come from for the potential? I see. Good. So remember, so let's first look at this term here. Where was it? Look at this term right here. It's a sum over lattice sites. Summing over lattice sites means that you need to sum over all locations on the lattice, which means you need to sum over all space-time points. And second of all, and think about this term here. Okay. Remember, we have a sum over all A and B that are neighboring sites. So you could think about that as a sum over A times the sum over all the neighbors of A for a given fixed A. You see what I mean? So it still involves a sum over A. And it's because of that sum over A that you get that integral d2x. I mean, we could all do this incredibly rigorously if we wanted to. I'm just trying to be a little heuristic here when I introduce this. But yes, good question. Other questions? Okay. What I'd like to do now is just introduce a little bit of notation that's going to make our lives much, much simpler. So in particular, in this class, I'm really going to be using a relativistic notation where space and time are treated on equal footing. So instead of using different symbols x and t to refer to space and time, I'm going to use the relativistic 4-vector notation, where I have a single symbol that I'll call x mu that describes both space and time. So here mu is an index, just like a vector index, except it now runs from 0 up to 3 rather than 1 up to 3, as with the usual 3 vectors that you are used to dealing with. And this symbol here just means that, say, x0 is equal to t, x1 is equal to x, x2 is equal to y, x3 is equal to z. And instead of referring separately to time derivatives and spatial derivatives, I'll just use a single symbol, d by dx mu, or d by partial sub mu, to refer to the 4 different derivatives in the time and the spatial directions. And that free index mu just is a label, so d0 is the time derivative, d1 is the derivative in the x direction, and so on and so forth. And finally, I'm going to introduce what's known as the metric of Minkowski space, which is a 4 by 4 matrix whose diagonal elements are 1 or minus 1, so that, for example, the term in the action that I wrote above, which was phi dot squared minus the gradient of phi squared, can be written more simply as the sum over mu and nu, g mu nu, d mu phi, d nu phi. So that's simple, but that's still not simple enough. So in particular, I'm also going to use what's known as Einstein's summation convention, or Einstein's summation notation, which is the statement that repeated indices are automatically summed over. So that I could just write this as g mu nu, d mu phi, d nu phi. Okay. And then rely on the fact that because mu and nu are repeated indices, they both appear twice, they're going to be summed over. And then I will use one more piece of notation, which is that indices will be raised and lowered using the metric g mu nu. So what do I mean by that? What I mean by that is that if I have a 4 vector, let's call it a mu, then I can define the 4 vector with an upper index as g mu nu a nu. Or similarly, if you have a 4 vector with an upper index, b nu or b mu, then I will define the 4 vector with the lower index as g mu nu times b nu. And g mu nu with 2 upper indices is the metric that I've written up here. And it's also going to be the same as the metric with lower indices. So, unfortunately, or fortunately, depending on your point of view, this means that the placement of indices, upper or lower, is going to be important in this course. Okay? Because there are minus signs that can appear depending on whether I have an upper index or a lower index. So, for example, x mu is the 4 vector whose components are t and x, and x lower mu will be the one whose components are t and minus x. If that's not totally obvious, just work it out using this summation right here. I will make one comment, which is that I'm using a particular convention for my metric here. So g mu nu, this 4 by 4 matrix, is referred to as the metric of flat space, the metric of Minkowski space. There are two competing conventions. One, the convention I'm using here is the so-called mostly minus convention, where it's 1, minus 1, minus 1, minus 1. The alternate convention is the minus 1, 1, 1, 1 convention, which just differs by a minus sign. So, half of the world uses mostly minus, half of the world uses mostly plus. The general relativity community tends to use mostly plus. I actually, in my research, tend to use mostly plus. Quantum field theory, particle physicists tend to use more mostly minus. So that's why I'm using mostly minus here. It kind of pains me to do so. It sort of hurts me every time I have to write down an equation in mostly minus signature. But there are a lot of equations, and it doesn't matter, it's just a convention. But there are a lot of equations that sort of look nicer and are easier to remember if you use the mostly minus convention. Okay, so I'm going to try and stick to that, but I promise I'm going to make mistakes, lots of mistakes, because in my head I'm translating between the two different conventions. But for example, most quantum field theory textbooks tend to use mostly minus, and I thought it would be sort of cruel of me to use a different convention in my lectures than in any of your textbooks. So for that reason, I'm going to try my best to stick to that convention. Just as a show of hands, how many people feel comfortable with Einstein summation notation? Okay, good, great, okay. Most of you, and if you aren't, you will be, okay. And how many of you feel comfortable with the metric of Minkowski space and all that stuff? Because I am going to need to do a bit of, we're going to get pretty heavy into the special relativity, so I'm trying to figure out exactly how much I need to review. Okay, I'll do a little bit of review, but not a ton of review. Good. Okay, so with this notation, our action is the integral d4x of the Lagrangian, and the Lagrangian is 1/2 times d mu phi minus 1/2 m squared phi squared. So that's the Lagrangian of what's known as a free Klein-Gordon field, or a free scalar field. And the parameter m is referred to as the mass of the field. And the reason why we call that parameter the mass of the field will hopefully become clear in the next, by the end of class today. Good. Okay. So this is the action. Let's go ahead and derive the equations of motion. So given an action, that's the integral of some Lagrangian, which is itself a function of the field and its first derivatives. How do we find the equations of motion? Well, just as in regular mechanics, in field theory, we find the equations of motion by varying our field and setting the first order variation of the action to be equal to 0. So this is just the usual principle, as true in field theory as it is in particle dynamics, that the motion of a system is determined by extremizing the action. It's determined by Euler's principle, or the action principle. Good, okay. So what's the variation of the action? Well, the variation of the action, if you vary the field by some infinitesimal amount, d phi, is the integral d4x of, well, the Lagrangian depends on phi and its derivatives. So you have a dl by d phi plus, well, now this symbol d mu phi is a symbol for 4 different derivatives. And so we need to calculate the derivative of the Lagrangian with respect to phi dot, d phi by dx1, d phi by dx2, d phi by dx3. So you get a sum of 4 terms, which are dl by d of d mu phi times the times the variation of phi in here times the variation of d mu phi. And as promised, I'm using Einstein summation notation here. So this is really secretly a sum of 4 terms, where mu is equal to 0, 1, 2, and 3. And I'm using the chain rule for derivatives, okay, to express the variation of the Lagrangian as the sum of the 4 derivatives. And now, just as I did in the case of a single variable, we integrate that guy by parts. So we take this term and we integrate it by parts. So I use the fact that the variation of the derivative of phi is the derivative of the variation of phi. Okay. So if phi is being varied, then the derivative of phi is being varied in such a way that the variation of the derivative of phi is the derivative of the variation of phi. If that's confusing, just don't think about it very hard. You either have to think about it very hard or not think about it very hard at all. If you think about it a medium amount, it's sort of confusing. So integrating by parts, we find the analog of the Euler-Lagrange equations for a classical field theory plus a boundary term, just as we did in classical theory, where now it's a boundary term involving four derivatives. So dl by d mu phi times delta phi. And just as we used the fundamental theorem of calculus to set this term equal to 0 for single particle mechanics, we can use Stokes' theorem, which says that the integral d4x of a gradient is equal to a boundary integral. Okay, this is either Stokes' theorem or Green's theorem. I never remember which one is which. But it's the statement that the integral, so you've seen it in vector calculus, the integral d3x of the gradient of a divergence is equal to the integral on the boundary of that region of the thing you were taking the divergence in of dotted into the normal vector of the boundary region. I can never remember all those divergences and gradients and stuff like that. That's why everyone should learn differential forms, but that's because it's much simpler if you think about it in terms of differential forms. But anyway, the point is that this is some boundary integral, and if I take my variation of the field to die off sufficiently quickly at the boundary, we could just set that equal to 0. So the variation is equal to 0 if the field phi satisfies the Euler-Lagrange equation, which is the equation of motion for your field phi, dl by d phi minus d by d mu, dl by d mu phi is equal to 0. Again, these are the sort of thing that's a little bit unfamiliar the first time you go through it, but it's really a completely straightforward generalization of single particle mechanics. And again, if this is not entirely clear to you, I recommend just going through in your head and thinking about replacing it phi, thinking of phi not as a continuous function, a function of continuous variables of x, but thinking of x as a bunch of lattice points, and just a degree of freedom phi for each lattice point. Good. So let's just work out this Euler-Lagrange equation in the case of our free scalar field. So here L was, or let's do a slightly more general case, because it's no more work. So let's take the case where the Lagrangian is that kinetic term that I wrote down earlier, and let's just for fun consider the case where you have not just a mass term, but some more complicated function of phi there. So this would be the case if we took our lattice of points, and instead of just taking that quadratic approximation, we included some higher order terms in the approximation. Still keeping then you would end up with terms. Well, you would end up with lots of different terms, but some of them would look like this potential that I've written down here. So this then would describe some sort of potential energy or I should really say a potential energy density associated with the field phi. And then what is the equation of motion? Well, the equation of motion says that dl by d phi, okay, so that's minus v prime of phi, is equal to minus d by dx mu of the derivative of the Lagrangian with respect to d mu phi. One has to be a little careful with one's index notation here because it's easy to continually reuse the indices and sort of make mistakes that way. So remember that in this equation here, the index mu is summed over. So it's what we often call a dummy index. You could call it whatever you like. You could call it alpha. You could call it beta. You could call it whatever you like. So here, in this expression, we have one dummy index here, mu that's summed over, another dummy index here, mu that's summed over. You want to keep in your mind that those are two different indices. You could call them alpha and beta if you like. So maybe what I'll do is I'll call this one alpha here. So you have a d. So yeah, let's call this alpha. So we'll write this as d by d mu. And then what do you get? Well, if you stare at it for a second, you'll see that there's two possible different terms. One where this alpha here is equal to mu, and then another where this alpha here is equal to mu. And both of them give contributions that are just d mu phi. Right? So just to work through that for a second, there's one term where this derivative says that you take a derivative here where that alpha is equal to phi, and then where that alpha is equal to mu, then that alpha's got to be equal to mu. And so you'll get 1/2 d mu phi because of that. And then because you're squaring it, you have a similar term from over there. Okay. So this will be your equations of motion. Don't worry if that manipulation was a little fast. You'll get plenty of practice deriving equations of motions from Lagrangians on this and all future problem sets. So, for example, if V is 1/2 m squared phi squared, so that was the case of the free Klein-Gordon field, then what is this equation? This equation is d mu phi plus m squared phi is equal to 0. Or writing that out a little bit, d by dt squared minus gradient squared of phi plus m squared phi is equal to 0. And as promised, this is the Klein-Gordon equation. So we see here that the Klein-Gordon equation is really nothing more, nothing less than the classical equation of some field phi that would describe, for example, the displacement of some lattice sites on or the displacement of some particles that are connected by springs on a square lattice. For fun, you could think about, for example, other sorts of cases where you could derive the same field theory by thinking about lattices. Think about a hexagonal lattice, for example. Try and figure out what the field theory is that you would get from that. Graphene, for example, is a hexagonal lattice. Okay. You should be able to convince yourselves that in a certain approximation, you should be able to get the exact same goddamn field equations from any sort of lattice. Graphene is actually sort of special. It turns out, graphene is kind of special because there are strong interactions and this sort of nearest neighbor approximation where you only keep the quadratic things. The quadratic piece of the potential is not a good approximation. Okay, so in fact, the dynamics of graphene is described by a quantum field theory at low energies, but it is not the Klein-Gordon scalar quantum field theory. Instead, it turns out to be what's known as a Dirac fermion, which actually is something we'll we'll study later on in this class. Good. Any questions before I continue? Good. Okay, so we have an equation of motion. So whenever someone hands you an equation of motion, you should solve it, if you can. So let's just review the solutions of this Klein-Gordon equation. So on the problem set, you'll describe the solutions of the lattice model, but here we're working out in the continuum formulation where you have the continuous field phi, and as promised, the solutions are going to be traveling waves. So how do we see that? Well, this is going to be presumably something that you may have already seen in your electromagnetism class. So let's just consider a solution of the form e to the I p dot x plus I omega t. And if you just act on this guy with this Klein-Gordon operator right here, what do you get? Well, every time you hit phi with a time derivative, you'll bring down a factor of I omega, and so you'll get an omega squared. And similarly, every time you hit it with a spatial derivative, you'll get a p squared. You'll bring down a p, so you'll get a p squared. And then you'll have a minus m squared. That minus sign coming relative to this equation here because you have the two factors of I, so there's some overall minus sign. And then the equation of motion sets it to 0. Or, another way of saying that is the solution is that the frequency depends on the momentum and is plus minus the square root of p squared plus m squared. This is why that parameter m is referred to as a mass, because you can recognize this as the equation for the energy of a particle in special relativity with mass m. So this is why m is a mass. This is the relativistic dispersion relation, i.e., the relationship between energy and momentum in special relativity. Good. Sometimes we like to make life a little bit simpler, our notation a little bit simpler, by introducing a momentum 4 vector to go along with the position 4 vector. Sorry, that's supposed to be momentum. P mu, whose first component is the frequency and whose other three components are the spatial momenta. And so then, in this notation, the solution is just e to the I p dot x, okay, where p dot x is an abbreviation for p mu x mu. Any questions so far? Now, the special feature of a free Klein-Gordon theory, which makes it so easy to study, is that the equations of motion are linear. And what that means is that you can take two solutions to the equations of motion and add them together and get a third solution to the equations of motion. Physically, what this means is that two propagating wave solutions of the Klein-Gordon equation don't interact with one another. Just like electromagnetism, you can shine a flashlight this way and shine a flashlight perpendicular to it, and they'll pass right through each other without interacting. That's the characteristic feature of a free field theory, or a linear field theory. So what this means is that a general solution can be expanded in in a basis of plane wave solutions. So in particular, a general solution to the equations of motion could be written as an integral d3p with a 2 pi squared there, 2 pi cubed there, that's really just conventions, times e to the I p dot x times some function a of p plus e to the minus I p dot x times a star of p. What is a of, so this is literally just the Fourier decomposition of your field phi. And so what am I doing here? So the e to the IPX's here, those are our solutions to the equations of motion. When I do this integral d3p, all I'm doing is I'm adding up a bunch of solutions to the equations of motion. P is a continuous variable, so I'm integrating over it rather than doing a discrete sum. A of p is just some arbitrary set of coefficients that I'm choosing. They're going to be functions of the 3 momentum p, because remember that you have one solution for each 3 momentum 3 vector p, and the 0 component omega is determined by the 3 vector p through this equation. That's why it's an integral d3p instead of an integral of d4p. And so the a of p's are just some arbitrary coefficients that I use to build up my solution. And then I've added in the complex conjugate here because my field phi is a real variable. Okay? Phi is a real number for each point in space-time. And so this will describe some sort of general wave packet that will be some linear superposition of a bunch of different plane waves. And if you've studied electromagnetism, this sort of thing will be very familiar to you. In fact, this is much simpler than how it works in electromagnetism. In electromagnetism, you have to deal with the fact that your electromagnetic field has various indices, and so you have different polarizations, and in fact you can have wave packets with different types of polarized light, linearly polarized, circularly polarized, etc. Here we're dealing with a scalar field. There's none of these indices floating around, and so the equations are a bit simpler. So this is where I wanted to end. When we quantize the theory, in fact, we're going to be coming back and revisiting this expansion of the field variable in terms of plane waves again and again and again. So if there's anything that's unclear, maybe now is a good time to ask questions about that. Okay, so as a reminder, there is no class on Tuesday. Sorry about that. I will see you Thursday.